we're going to look at gravity. But we're looking at the force of gravity. And you may say, well, miss, we already learned gravity. No, what you learned was the acceleration due to gravity. So if you go back and look at our notes in kinematics, we were really talking about acceleration. In other words, we were looking at how fast an object speeds up. Okay, that's what we're looking at, the acceleration because of gravity. Okay, how fast that object speed up. We weren't actually looking at gravity. So today we want to know, well, how hard, what's that force that gravity applies to an object? So again, we know that objects are falling or accelerate due to gravity, but what's the magnitude of that force? How hard is it pulling? Okay, so let's take a look at an example. So a 5-kilogram box is falling through the air. What is the force of gravity acting on it? So here's the box. If I draw a free body diagram of the box, and I say, well, the box is falling through the air. Let's imagine it's a vacuum. So instead of air, let's call it a vacuum. Okay? So the only force acting on the object is gravity. We'll make this positive, and that negative. So if we look at the net force acting on the object, well, the net force is just gravity. That's the only force that's acting on it. Now, we don't have a number for it, but maybe we can figure it out. We know that this equals ma, because that's Newton's second law. And in this case, because it's falling, we know A is equal to G, which is equal to 9.8 meters per second squared. So this is going to equal to 5. This is 9.8. That's Fg. And therefore, the force of gravity is equal to 49 newtons. So based on this diagram, we can see that the Earth pulls down on that box with a force of 49 newtons. That's how hard it's pulling down. So based on what we calculated here, what we know is that Fg, the force of gravity, is really equal to mg, mass times the acceleration due to gravity. And this is our equation, okay, for force of gravity. Let's look at this concept of weight versus mass. If you were at home and you asked somebody who's not a physicist and you said, what's the difference between the two? They would say it's the same thing. Your weight is your mass and your mass is your weight. But in physics, that's not the case, right? In physics, we use two different definitions. So weight of an object is the force of gravity. So Fg is also equal to weight, right? And that's expressed in newtons. In other words, weight is a force, and it's newtons. Now, why is that important? Well, it turns out that the weight of an object can change depending on your location. So, for example, an astronaut will weigh less on the moon than it does here on Earth. Why? Because the moon is small, and the Earth is big, and therefore the Earth has more gravity. So here's the astronaut. The Earth will pull down harder, whereas here the astronaut, and somehow the astronaut shrunk as well, which it shouldn't. The moon does not pull down as hard, right? And so you actually weigh less, you have a smaller force on you than on Earth. Okay, and that's why you weigh less on the moon. If you went to a bigger planet, like say Saturn, which is much bigger than what I've drawn, then you will feel you have a much higher force, and you'd actually feel heavier. Mass, on the other hand, is a measure of the amount of matter in an object. It's measured in kilograms, and so it will not change. So a 90-kilogram astronaut is still going to be 90 kilograms whether he's on the moon or the Earth. The amount of matter doesn't change. Okay? So mass is the amount of matter. Gravity is a force. Okay, so that's the distinction between the two. This is in kilograms. This is in newtons. This is always constant, unless you lose weight, I guess. If you, see, there's where the confusion comes in, unless you lose mass, okay? And this can change. So the question is, well, why do we always mix them up? Well, we use them interchangeably because gravity is pretty much constant on the surface of the Earth, right? So your weight doesn't change, right? And therefore, weight and mass, people use them interchangeably, right? Because really, the only time your gravity, your weight would change, right? The only time your weight would change is if you are on the moon or on Saturn. Well, how many of us have been to the moon? Very few. I think there's about 4 people who've ever been to the moon. Okay, the rest of us, we're here on Earth. And so that's why we sort of use these interchangeably. But in physics, they're 2 different things. Now, the normal force, as I've said before, is the force acting between an object and the surface it is on. So for example, for you right now, here's you. This is a free body diagram of you. You have the chair that's applying a normal force to you right now. And then you have gravity that's applying a force downwards on you, right? So on a horizontal surface, so if you're not sitting on a slant or something like that, the normal force is equal to, but opposite in direction of the force of gravity. So whatever this is, and whatever this is balanced out. And that's why you're not like falling through your chair or moving, right? You are maintaining a constant velocity because of that. There are times, though, when the normal force won't equal gravity. And that happens if you happen to be in something that's changing its speed. So if an object is moving in the vertical direction like an elevator, so let's say you're in an elevator, then the normal force is not equal to gravity. So let's say this is the elevator, and here's you inside the elevator, right? If you're just standing inside an elevator that's not moving, then the normal force acting on you, that's from the floor of the elevator, is balanced out by gravity, right? And those 2 are equal. Okay, but if you are in an elevator that's accelerating upwards, so here you are on the elevator, well, what's going to happen is that the floor of the elevator is going to push up harder on you. Your gravity doesn't change because the Earth is still pulling the same amount. And so your Fn is higher. So Fn is bigger than the force of gravity. So what does that do to us if you have an Fn that's higher? How do we feel that might be different? So it turns out that what we feel as weight, we're actually feeling the Fn, the normal force. Okay, you can't feel gravity pulling down on you. What you feel is the floor pushing up on you. And that's what we sense as weight. All right, we actually sense Fn. And so what happens is if you happen to be falling, so let's imagine you're falling through the air, there's no Fn. There is gravity pulling down on you, that's why you're falling, but there's no Fn. That doesn't exist. You actually feel weightless, right? This is why you feel weightless. You're not actually weightless. Gravity is pulling on you, but our body has nothing to sense, all right? So that brings about something called apparent weight, because sometimes we feel like we weigh heavier than we actually do, right? And that happens in vertically accelerating objects like elevators, okay? Or roller coasters, right? So your weight appears lighter or heavier depending on the direction of acceleration. So let's take a look at this example. So we have here a man, okay, a 70 kilogram man, so there's his mass, 70.0 kilograms. He's standing on an elevator that is accelerating upwards at 1.2 meters per second squared. And so we want to find his apparent weight. So what weight does he feel? Does he feel heavier? Does he feel lighter? What does he actually feel? Okay, so what we have to do, because it's a forces question, we have to draw a free body diagram of the man. Okay, not of the elevator. We want to know his weight, not the elevator's weight. So if I draw a free body diagram, well, what are the forces acting on the man? If you're in an elevator, what's acting on you? Well, obviously gravity, okay, and the floor of the elevator is pushing up on you. So those are the two forces. If you're standing in an elevator by yourself, those are the two forces acting on you. If we set up, well, let's set up direction. So the elevator's going upwards, so that means the man's going upwards, so we'll make up positive. Okay, so if that's the case, let's set up our F net equation. And what are the forces acting? Well, Fn, we don't have a number for it yet. And Fg, we also don't have a number for it, but maybe we can figure one out. We know F net is equal to mass times acceleration. We know Fn is what we're looking for because we're looking for how he apparently weighs. And we are looking for, we have gravity, right? Fg is equal to mg. That's our new equation that we just learned. I should be able to plug in a number for F net. So that's going to be 70 times 1.2. I should also be able to figure out what Fg is, and that's going to be 70 times 9.8. So that's going to be, let's see, 70 times 1.2, so that's going to be 84. And 70 times 9.8, that's going to be 686. Okay, and therefore Fn is equal to 686 plus 84, which is 770 newtons. So therefore, the man feels like he weighs 770 newtons. That's his apparent weight. Okay? Now, for all of us, you're like, oh my God, 770 newtons? No, it's weight, not mass. We never really talk about weight in newtons. Right? So if I asked you, oh, how many newtons do you weigh? You're like, I don't know. I weigh 60 kilos. Or I weigh 120 pounds. We don't really know what 770 newtons means. Okay? We don't normally speak in this, right? It's not common to use weight as a measurement for how heavy we are. So what I've asked you to do is I say, well, what would the mass to 770 be? So if a person has a weight equal to 770 newtons, what is the mass for that? Okay? Well, we just had our equation Fg equals mg. We know this equation, we just learned it. Well, I told you that Fg is weight. And m is mass, which is what we're looking for. So if I use this equation, I should be able to figure it out. So this is going to be 770. Mass, g is 9.8. So therefore, the mass is 770 divided by 9.8, which is 78.57 kilos, which after sig digs, I think it's 2, so it's going to be 78 kilograms. So therefore, if someone has a mass, if someone has a weight of 770 newtons, that's equal to 78 kilograms. In other words, the man has a mass of 70 kilograms, but feels like 78 kilograms. So he feels 8 kilos heavier. In case you're wondering, 70 is 154 pounds. So if you're used to using pounds, but 78 is 172 pounds. So he weighs about 18 pounds heavier. All right, that's what it is. Just by going up on this elevator. He feels like he weighs 18 pounds heavier. He isn't actually 18 pounds heavier. Okay, you don't just gain weight by going up an elevator. Well, you do, but you don't gain mass. All right, so that's the end of this lesson, and I'll see you guys at our next video.